Hi, I want to show you how we deploy a network service called the Elastic Router using an orchestration framework called UNIFY. We will deploy the service, scale it, and show the use of automated monitoring and troubleshooting tools. On a high level, the service is described as a service graph with one functional block, routing traffic between 4 access points. This service graph is sent to an orchestrator where it's decomposed into discrete VNFs, which are really, in practice, implementable network functions, which can be deployed on the available infrastructure or servers which are available to the orchestrator. I will now start the orchestrator in a different machine, and I will send it the service graph, which describes this monolithic Elastic Router. And then I show that we have implemented a database, a Neo4j graph database, which translates this single monolithic Elastic Router block into 2 discrete VNFs, which is a control plane and a data plane. And those 2 VNFs are then sent back to the orchestrator, and the orchestrator will deploy those 2 discrete VNFs further onto the infrastructure. So here you see in the database how this is stored. One Elastic Router block is decomposed into 2 single VNFs connected together. I will now, with a simple call command, post the service graph to the orchestrator. The orchestrator will contact the infrastructure which is available, see which resources are available, and map then the new network functions onto the available server. And we see that in the web GUI of the server, indeed, different network functions have been deployed. Also, the VNF which implements the control plane of this service has a web GUI, and in this one we see that it has detected one data plane which has come up and has been installed also on the server. Now, in this orchestration framework, we also implemented different monitoring tools, which you can see the output of in the Grafana figures on the bottom of the screen. So we have 4 different metrics which are being measured and being displayed here. Next, I will start a traffic generator, which will start some traffic and will generate some load to our service. And this we will see by an increased measurement of the CPU load on the right side of the graphs, the upper right graph. The lower right graph is displaying the packet rate, which you see increasing. And on the left side, those 2 graphs are a specialized metric, which we have installed in this framework, which shows the risk of overloading our network service, which is statistically calculated and measured. Here you see some logs of messages that are used to start up different monitoring parts of the framework. Meanwhile, the traffic generator has started to increase the traffic load, which is visible in the CPU load, which is rising, and also the packet rate, which is rising. This is detected by the monitoring framework, and once it reaches a certain threshold, this monitoring framework generates a scaling trigger to the control plane of our service. And this control plane then instructs the orchestrator to add more resources, basically to scale out the existing service. Here we see again some logs of messages being sent to instruct the monitoring framework to add more monitoring to the added resources. So in the web GUI of the control app or the control plane of the service, we see that it has scaled out using 4 data planes instead of the original 1 data plane when there was less traffic. This is also visible on the Grafana figures, where you see now 4 lines, each line representing 1 data plane. In the architecture of this orchestration framework, we have foreseen a secure message bus which transfers the metrics from the functional blocks who measure them to a database that stores them, and also transfers the generated triggers or alarms that instruct, for example, the scaling. Next, we will introduce a bug into the routing table of OVS5, one of the data planes in our service. And then we rely on our troubleshooting framework called epoxide to find that bug automatically. Epoxide executes other troubleshooting tools to identify this fault. In each sub-window, epoxide shows relevant information about its sub-processes. High-level logs are always presented in the top left sub-window. When our monitoring tools detect an imbalanced state, they notify the troubleshooting framework, as you can see from the log message of epoxide highlighted in yellow. And then first, epoxide calls a tool called RQE to check the CPU loads of the different data planes. As you can see, the error that we introduced causes an imbalance in the service. You can observe this on the Grafana window. The top left chart shows an aggregated imbalance metric calculated statistically, while the right-hand side displays the CPU loads and traffic rates of the different data planes. The imbalance was detected by the monitoring tools, and they sent a troubleshooting trigger as seen previously. As you can see on the slides, the effect of inserting this bug in OVS5 translates to an increased CPU load of several data plane processes, and also an increased traffic rate on several links in the service, which is also visible on the Grafana figures. Here we see an overview of the total architecture with all the components that are interacting with each other. So there is a tool called RQE, and when this one finds an intolerable imbalance in the service, epoxide gives an alarm shown by the desktop notification you see in the right corner. And at this point, epoxide configures another tool called AutoTPG in order to verify the routing tables of all the data planes. So after AutoTPG has been initialized, it verifies every data plane one by one, starting with OVS5. As you can see on the slide, AutoTPG has a direct interface into the deployed VNFs to check its internal state, or routing table in this case. And once the error is found, a notification is given, but the execution continues by verifying the other data planes, while simultaneously querying the routing table of the faulty one. The identification of the fault itself, being the error in the routing table, is now the job of a human operator who can analyze the open flow entries as displayed by epoxide. So having located the source of the imbalance, the troubleshooter should now manually fix the bug. We skip this step by running a custom-made script from epoxide in this demo. So after executing the script, the routing tables are being brought back to a normal situation, the bug is fixed. And if you now look at the Grafana charts at the bottom of the screen, you can see that the imbalance gradually decreases, and the metrics again converge to a normalized balanced state as it was at the beginning before the bug was introduced. So once everything is normalized again, this will be detected by the monitoring framework, and this will generate a trigger to epoxide to instruct it to stop the troubleshooting procedure. So the CPU load and traffic rate is normalizing again, the balanced state of the elastic router is again normal, and we can now query the routing table of the previously faulty data plane, and you can see that the faulty entries are gone now. So if we try to manually restart the troubleshooting process once again, we find that the elastic router is no longer in an imbalanced state, as detected by our monitoring and troubleshooting framework. So here we show an excerpt out of the definition file which described our troubleshooting process, and this domain-specific language that was used for this is based on the syntax of the click language. So this describes the complete workflow of the troubleshooting procedure. So this demo showcased the integration done during the UNIFY project, and this demo was a specific cooperation between different work packages. I hope this has been informative, and thank you.